Okay, so now I want to talk about one of my favourite kinds of surfaces, which is the projective plane. The projective plane is very, very strange in some respects. It's very different to the kinds of spheres and toruses and things which one normally encounters as surfaces, but it's also very, very important. And if you look at it in the right way, it's really not that complicated. And also it's related to some really important kind of classical mathematical ideas. Now, the term projective plane conjures up all kinds of ideas about perspective drawing and geometry and all the rest of it, but I just want to talk about this thing as a surface. Okay then, so what is the projective plane? What kind of surface is it? What does it look like? Well, it doesn't look like a torus, it doesn't look like a sphere. It has some similarities to a Mobius strip. I'd say a nice way to start describing it to the layman would be to say that it's a kind of twisted sphere. Alright, so let's think about the sphere. You can represent the sphere in a nice kind of two-dimensional way by making a sort of picture like this, okay? So the idea here is that we have all these points. So this is just a disk, of course, just a disk, and we have these points, 1, 2, 3, 4. And if we identify these points, if we glue them to these ones here, we get a sphere, okay? So if we literally just kind of stick these things together, so we stick the 1 to the 1 and the 2 to the 2 and the 3 to the 3, and we do it for all these points around here, we end up getting a sphere. Okay, so we can see that a sphere you can basically get by taking a disk and gluing these points along these lines. Okay, now to get a projective plane, basically exactly the same kind of operation, except we're gluing diametrically opposite points. So this is for the projective plane, okay? So here, like, let's compare, okay? See here, on this one, this is the sphere. Let's just verify. Sphere, projective plane, okay? So, on here, on the sphere, this 1 glues to this 1 close by, this 2 glues to this 2 close by, etc. Whereas on the projective plane, we're gluing together diametrically opposite points. So this 1 should be glued to this 1 dash here. This 2 should be glued to this 2 dash here, and so on and so forth. And so if you actually try and do this, you're going to run into some difficulties, because actually if you try and do it in 3D space, you find that things go a bit funny, and the paper starts kind of crossing with itself. Okay, so another sort of more physical way that you can get a model of a projective plane is by gluing together a Mobius band and a disk. Now this is a very strange idea, because when you look at a Mobius band you think, how the heck can I attach this to a disk? Well, the thing is with the Mobius band, it actually only has one edge, okay? I mean, it's twisted. I mean, remember, the Mobius band is just what you get from taking a piece of paper, twisting it half and gluing it together, right? So let me just sort of give you a visual proof that it only has one edge. I'm just going to draw along this edge, colour it in, and you'll see that we've only got one. If we just carry on going, see, we just keep colouring along, trying to do this so it's still visible on the camera. We're keeping going. Keeping going. And there we have it. All I've done is just keep colouring that same edge, and we've gone all the way back around to the start. So what does that mean? Well, what that means is that the boundary of this shape is a circle. I mean, a sphere doesn't have a boundary. A cylinder has two circles as boundaries, but the Mobius strip, it only has one circle as a boundary. And so, theoretically, we can glue that circle to the circle on the outside of that disc. I mean, if we actually try and do it, we're going to run into some difficulties, right? I mean, let's have a go. So we start trying to glue this disc, and very quickly we start to realise that it's going to be a bit tricky, and in fact, like intersections and things start to appear. So it's a kind of thing that's, again, difficult to do in three-dimensional space. Okay, so we can basically think of the projective plane like this, as a disc with these opposite points identified. Now, we can also draw it like this. It's basically the same idea, we've just made it into a square instead. I mean, we're allowed to do that in topology. So, basically, we have these points along the top, and sort of this point would be identified with this point would be identified with this point, etc. So again, we're sort of identifying kind of diametrically opposite points, except that we've made everything square now. Now the reason we're doing this is to show that there's another way to think about the projective plane. And basically the idea is that actually another good way to think of a projective plane is that it's actually the thing that you get by taking a Mobius strip and gluing it to a disc. So let me see if I can give you a quick proof of this, okay? So basically, here's our projective plane, and we're going to do a little bit of surgery. Okay, so let's cut out this middle bit. We'll cut out this middle bit. So basically what we're doing here, we're just cutting along here, and we'll cut again. Let's cut out this bit here. So here we are, we've made these cuts, and so now we can take out this middle part here. So what we're essentially doing is kind of cutting a piece away from our projective plane. So let's just go ahead and do that, and pull this out. So what have we taken away, and what do we have left? Well, what's this that we've taken away? It's a Mobius strip, isn't it? This is a Mobius strip. It has these boundaries, well, boundary, and this should be going in this direction, and this should be going in this direction. So, actually, if we want to make this properly, we ought to identify it like that. So, this is essentially a Mobius strip which we've cut out. So after we've removed this this Mobius strip from the middle here, we can see that these are the two pieces that we're left with. Okay, so if we just attach these A's along the line as they should be, and we can glue these B's and such, then we're just left with this kind of open boundary at the top here. So we've kind of got this sort of like a boat shape, I suppose, where we've just basically got a disc as a boundary. So essentially we see that the projective plane is just a disc glued to a Mobius strip. So now our challenge of understanding what a Mobius what a Mobius strip is basically just boils down to thinking about how we can identify, how we can glue together this with this, right? It's not really very easy to think about, because although the Mobius strip does have a circular boundary, it's kind of twisted up, so there's going to be some self-intersections. But there's some wonderful drawings that you can see, which kind of show how you can kind of warp this Mobius strip so that it does actually have a circular boundary. And if you do that, you get something which is called a crosscap. A crosscap is a very, very important idea in mathematics, and you can make them out of blue tack, and you can make them out of different things. And so, rather than explain exactly how a Mobius strip can be changed into a crosscap, I just want to show you this very illustrative picture from this wonderful book called Euler's Gem, which is a really great recent book on popular topology, I suppose. Anyway, here they show how one can take a Mobius strip and one can warp it into this thing which is a crosscap. Basically, the crosscap is like a Mobius strip, except it has a circular boundary at the bottom. And to do this from a Mobius strip, you actually have to make this Mobius strip pass through itself. And you end up with this thing here, which is called a crosscap. So I'll show you some 3D pictures of this sort of thing later. Okay, so what I did was I 3D printed one of these crosscaps. It was pretty easy. I just got standard parameterization and then used Mathematica to make it into a model and then print it. And so here we are. Actually, this is actually a complete projective plane, because like this top part here, this sort of everything above my finger, let me turn around, it looks the same on the other side, that's really the crosscap. But then the crosscap's been sort of connected together again with a kind of disc, and that's filled it in and made it into a complete projective plane. And so this kind of top part here, this is the crosscap, this is the part that's equivalent to the Mobius strip. And so if one were to take a sharp knife and cut along here and then remove this top part, that would be the crosscap, and that would be topologically equivalent to a Mobius strip, as you've just seen by those pictures before. So basically the idea of a crosscap is that you've got this funny kind of chasm here and these two kind of places, and you can go from one side to the other in different ways. So if you're a little ant or something, a little two-dimensional creature, you can go from here to here just like this, and that's fine. It's just like walking around on a sphere or a plane. You don't change your orientation or anything else. Another thing you could do though is that you could go straight through this kind of chasm here, and then you'd end up, so if you look at it from the top, you see that coming along this surface here, you end up along here. So if you go through this chasm here, you end up coming out on the other side like so. And also in a sense you end up coming out inside the surface. So you're sort of inside this this surface now, and if you then wander around like this, you would be here, but you'd be kind of on the opposite side of the surface, so your orientation would be reversed. It doesn't really make sense to think of sides of surfaces, but you can think that there's two ways to get from here to here. One way would preserve your orientation, in the sense that if you had a circle which was orientated this way, and you sort of moved it like this, it would still be a surface which was orientated this way. But if you decided to take a different route and go through this chasm, and then you're on the inside of this surface here, and you wander around here, then you your orientation would be reversed. So what I'm mostly going to be doing is working with a kind of discrete version of this model. I kind of prefer this model here. It looks quite a lot worse, but it's actually a lot easier to make, it's a lot easier to think about, and it's basically very similar, at least topologically speaking. So you can see at the top of here, for example, we have this surface here that it kind of comes in like this, and then it intersects, and we've got another surface intersecting like that. We've got this kind of cross, and similarly we have a kind of cross going on here. So I mean, basically this is just a kind of discrete, kind of blocky version of this model here. If one was a little 2D creature, just like before, as I was saying, one could walk around here. There'd be two different ways to get from here to here. One could go the kind of normal routes along here, or one could walk through this kind of chasm here, in which case one would essentially be on this surface here, and one would sort of intersect through here and end up on the opposite side. In fact, as I was trying to say before with the other model, one would actually end up inside here. So one would kind of go along here and then actually inside this surface, in a sense. And so basically, hopefully you can see that this is just a discrete kind of version of this projective plane model here. And it also has the advantage that it's very, very easy to make. It's basically just like a couple of wedges with a snip. Okay, so the idea of this shape is it's basically just like a wedge. You know, it's kind of like a sphere at the bottom. It's just a wedge, except that we've got this funny thing going on at the top. And the way to think of it is that at the top we actually have these kind of self-intersecting surfaces, so that if you were walking along here as a two-dimensional creature, once you get to this snip point here, you actually carry on the bottom of the other side, so you end up kind of here on the opposite side. So another way to think of it is that if I just took this object here, if I just cut off this top part here, it would look something like this, okay? So for example, if you were coming up here, that would be like, let's see if I can hold both of these at the same time. If you were coming up here, that would be like coming up here, and then as you cross this place here, that would be like crossing over here and ending up on the bottom of here. So in a sense, you could think that when you cross this kind of chasm here, say you were on the outside, then you cross this chasm, you then end up on the inside. So you're here for a start, and then you end up on the inside of the opposite part. So then you could be walking around on the inside of this shape. And so, you know, you could walk around as if it was a sphere and do all kinds of things down here, but again, once you cross this chasm in the middle here, you would go from the outside to the inside, or the inside to the outside. Now, it doesn't really make sense to think of these kind of surfaces in terms of insides and outsides, but it kind of helps in a way to think about orientability like that. I mean, it's best to imagine a surface like this has been completely transparent. And then you can see that it's non-orientable as well, because, for example, if you drew some kind of circular orientation, like say this, okay, let's say this was some kind of hurricane spinning on this two-dimensional surface, it's spinning in this direction. Now, if a hurricane slides over here and goes inside this chasm, I'm calling it a chasm, I should probably think of a better word, but anyway, goes inside this chasm, and maybe the hurricane kind of goes down here and does some stuff, and it ends up on the opposite side to here, it would look like it was spinning in the opposite direction. In other words, if you think of it as a transparent surface, you can see that essentially crossing that chasm changes the orientability of the surface, much like going around a Mobius strip changes the orientability of the surface. So this is my kind of personal interpretation of the projective plane. I've kind of tried to expand out on this model here. Basically all I've done is replace this idea of a wedge, which sort of subtly represents a self-intersection, with a much more kind of in-your-face looking self-intersection like this, which you know, basically involves these different stripes. So for example, this this strip here, this goes from the outside of this wedge on the right to the inside of this wedge on the left. And so if one moves from one wedge to the other across one of these strips, in other words, if one moves from one strip to the other using the top part of here, then one ends up kind of on the opposite side of the surface. So if one was on the outside here and one goes across here, one would be inside, one would be on the inside of here, and vice versa. However, if one wishes to move from one wedge to the other wedge without having their orientation reversed, or equivalently their kind of side changed, one could always go down below this this kind of place. So hopefully you can see the kind of the similarity. You know, the wedges represented by this and this, the chasm here represented by these strips, and this part here where you can move around without losing orientability are represented by this part here.